Hi, in this video, we're going to go over the solutions for this week's discussion handout, which is on Markov decision processes. The question on this worksheet is going to be about a mini version of blackjack. Here's the setup of the problem. Every turn, you can either draw or stop. If you draw, you have an equal chance of getting either a 2, a 3, or a 4. And you get no immediate rewards when you draw. If you stop, you get a reward equal to the total number of points that you have in your hand. And if you have 6 or more points in your hand, the game immediately ends and you receive a utility of 0. So we can formulate this as a Markov decision process. The states that we have correspond to the number of points that we can currently have in our hand. And in this game, the states are 0, 2, 3, 4, and 5. We add a done state, which handles the case when we have 6 or more points and the game ends, and also when we take the stop action and end the game. There's no discount in this MDP, so the gamma factor is 1. The first question asks us to define the transition function and the reward function. Remember that both of these functions take in 3 arguments: the starting state, the action taken from the starting state, and the successor state. Let's start off with the reward function, because that one's a little bit simpler to define. We only get a reward when we take the stop action from some state that we have, and we land in the done state. This reward is equal to the total number of points that we have in our hand, which is just equal to S. And then let's make a note here that S has to be in one of our legal states. In other words, it can't be the done state. For any other S prime triple, the reward is just going to be 0. And there's our reward function. The transition function gives us the probability of transitioning into some successor state S prime after committing to some action A from some state S. So let's see what kinds of transitions we have. Let's start with something easy. What's the probability that we land in the done state, given that we took the action stop from a state S, where S is one of our non-terminal states, so 0, 2, 3, 4, and 5. Well, the stop action always succeeds, so this probability is 1. Okay, so now let's think about the case where we start at 0, we take the action draw, and we land in some state S prime. Well, what states can we land in? We can land in 2, 3, and 4. And each of these occurs with probability 1/3. Now let's consider starting at 2 and taking the action draw. In this case, the possible successor states are 4 if we draw a 2, 5 if we draw a 3, and we land in the done state if we draw a 4. And each of these also occurs with probability 1/3. Starting at 3 and taking the action draw, what successor states can we land in? Well, we can land in state 5 if we draw a 2, and that happens 1/3 of the time. If we draw a 3 or 4, we land in the done state, and that occurs 2/3 of the time. So there we have 2 cases for this transition. Starting at state 4 and taking the action draw, we're guaranteed to land in the done state, so this probability is 1. Same thing applies if we start at 5. So these are the valid transitions. Everything else just gets assigned to 0. And that's the whole transition function. For part 2, we're asked to run value iteration to compute the optimal values for each state. The equation for value iteration is posted right here for your reference. The value of a state is the optimal expected sum of discounted rewards acting in the MDP. For value iteration, we consider values of the form v sub k of s, and the meaning of this is, what's my optimal expected sum of discounted rewards, starting from state S and having k time steps left to move in the MDP. So in this problem, when we look at how to compute these v sub k values, for some examples, I'll work through an intuitive verbal approach, and for other examples, I'll work out the math behind the value iteration update. Okay, so value iteration begins by setting v0 equal to 0 for all states in the MDP. This is because with 0 time steps left, you can't achieve any rewards because you can't take any actions to get any rewards. So that's why this first row here has all zeros. So just as a reminder, at each iteration for value iteration, we compute the update for all of our possible states, and only after that can we move on to the next iteration. This is because the next iteration will depend solely on the values on the current iteration. In this table here, that means that we can only continue to the next row after we have completed the whole row above. So we're done with the v sub 0 row, and now we can go on to the v sub 1 row. In this row, we're considering what's the best sum of values we can get with only one move to make. Remember that we can only get rewards if we stop, and so with one move to make, with the exception of state 0, we can get a non-zero reward if we stop. So we should prefer stopping for states 2 to 5. And the value you get for stopping is the number of points that you have, so we can easily fill out this row. 2, 3, 4, and 5. For state 0, it doesn't really matter if we draw or stop. Either way, we're going to get a reward of 0. Now things start to get interesting at the v sub 2 row. At the v sub 2 row, we have 2 time steps left to act on, and the values we calculate here will depend on the move we make now and the values that we computed for v sub 1. Let's start from the right. At state 5, with 2 moves left to do, what should you do? Well, you should stop, since drawing will cause you to get more than 6 cards and immediately end the game, getting a reward of 0. The value that we get by stopping here is going to be 5. Same logic applies for state 4, so let's put a 4 in this box. Alright, now we get to state 3. Here maybe it's not too intuitive whether we should stop or draw, and so let's pull out the value iteration equation. The value at state 3 with 2 time steps left to go is going to be a max over 2 different values corresponding to the stop action and the draw action. For the stop action, we need to take a sum over its successors. Well, if you stop from any state, you're going to land in the done state, and so there's only one successor. The sum pretty much drops out. Then what we have left is the transition from state 3, taking the action stop and landing in the done state. That transition probability is 1. Now we have to consider the reward of starting at 3, taking the action stop, and landing in the done state. And then we have to add to that the discount factor times the value with 1 time step left of the landing state, which is the done state. The value of the done state is always 0 because you can't get any rewards. This gamma term is 1 because there's no discounting. And the reward you get for stopping at starting from state 3 is just going to be 3. So we have 1 times 3 plus 1 times 0, and this is just going to be equal to 3. Well, that's expected, right? Because if you stop at state 3, you end the game and you get the reward of 3. Okay, so now we need to consider the value of the draw action. The successors from starting at 3 and taking the action draw is going to be 5 if you draw a 2, and the done state if you draw a 3 or 4. So we'll have 2 different terms in this sum. Let's start with the landing state of 5 first. So we want the transition probability of landing at 5 from state 3 and drawing. It's multiplied by the reward from starting at 3, drawing, and landing at 5, plus gamma times your value with 1 time step left if you start at 5. And then the other term is just going to be similar, but the 5 just gets replaced by the done state. So let's write that here. R of 3 draw done plus gamma v1 of done. And what we need to do here is we need to substitute in values. So the transition to state 5 happens with 1/3 probability. The reward you get for drawing is 0. Your gamma factor is 1. And your value at 5, we can read that off. That's just 5. So let's put a 5 here. The transition to the done state happens the other 2/3 of the time. So let's put 2/3. The reward you get for drawing is 0. Your gamma factor is 1. And the value at a done state is 0. So this term drops out because of 0. And all we're left with is 5/3. Back here we take the max of 3 and 5/3. So 3 wins. And we get a value of 3. That means that stop is more favorable than drawing. And we can put a 3 in this box. Now let's look at calculating v sub 2 for state 2. Again, it might not be too intuitive whether we should stop or draw, so let's again consider the Bellman update. Let's start off by writing v sub 2 of 2. Again, it's going to be a max over the possible actions, which is stop and draw. The stop one's pretty similar to this case up here, and we're just going to get a reward of 2 when we stop. For the draw action, we have to consider the successor states from starting at 2 and drawing. So if you start at 2, you can draw a 2 and land in state 4, you can draw a 3 and land in state 5, or you can draw a 4 and land in the done state. So we have 3 different terms in this sum here. So let's write this down here. This is going to be a sum over t of 2, draw, and 4, plus the reward 2, draw, 4, plus gamma times v1 of 4, plus t of 2, draw, 5, times the reward of 2, draw, 5, plus gamma v1 of 5, plus t of 2, draw, done, plus the reward of 2, draw, done, plus gamma times v1 of done. And we have all these values for us. Each of these terms is 1/3. The rewards for drawing are all 0. And all the gammas are 1. And so basically what it comes out to be is an average of these terms here. This one's 4, this is 5, and this is 0. So the average of 4, 5, and 0 is going to be 3. And so we end up with 3 here. We prefer the 3 over 2 because 3 is higher. And so the value at 2 is equal to 3. And we'll put a 3 up here. Okay, so before we go on, for this MDP, hopefully you can see the pattern here. We're maximizing over the value that you get if you just stop with your current hand, which is just equal to the total number of points that you have in your hand, and the value of the draw action. This value is going to be the expectation of the successor state values in the previous row in the table up here. So this doesn't always happen for a general MDP. The reason why this behavior occurs is because the draw action doesn't produce any immediate reward. So all the RSAS prime terms for the draw action, these are all 0, which is why we can take the expectation of the future terms. And of course, this gamma is also 1. Had there been some value for drawing, we have to include that in our calculation. So it will no longer look like a simple procedure for reading averages on the previous row. So be careful with that. So with this reasoning, I'll speed it up a bit. For v sub 2 of 0, we should obviously draw since we can get some value by stopping at the next move. The value corresponding to the draw action is going to be the average of the v sub 1 values for the successor states, which are v sub 1 of 2, v sub 1 of 3, and v sub 1 of 4. So we take an average of 2, 3, and 4. That gives us 3. And so the value v sub 2 of 0 is going to be 3. We're done with the v sub 2 row, so now we can move on to the v sub 3 row. Here, the extra time step doesn't change the value for v sub 3 of 3, v sub 3 of 4, and v sub 3 of 5, since it preferred stop before, and it will continue wanting to stop, so we can just copy the values down here. So let's just write 3, 4, and 5 here. For v sub 3 of 2, we take an average between the v sub 2 values for the successor states, which are 4, 5, and the done state. Reading that off is an average between 4, 5, and 0, so that's 3. And that's the value you get for drawing. You get a value of 2 for stopping, so it will prefer the value of 3 since it's higher, and hence this value did not change. For v sub 3 of 0, obviously we want to draw here, so we take an average between the v sub 2 values of the successor states, which are 2, 3, and 4. Hence, we take an average between 3, 3, and 4, and so we end up with 10/3 as the value for v sub 3 of 0. The small increase in value here comes from the fact that if you started from 0, drew, and landed at 2, well, now you have this extra time step to draw again from 2, since drawing from 2 is optimal. And if you drew from 2 on expectation, you'll get a slightly higher reward than if you had stopped at 2. For v sub 4, we have the same reasoning as the previous step for states 3, 4, and 5, so we'll just copy down the values here. Calculating v sub 4 of 2, we need to take an average between the v sub 3 values of the successor states, so we want the value of 4, the value of 5, and the done value, which is 0. Hence, the average of 4, 5, and 0 is still going to be 3. To calculate v sub 4 of 0, again, we want the average of the v sub 3 values of the successor states, which are 2, 3, and 4. So an average between 3, 3, and 4 is just going to be 10/3. Here, notice that none of the values have changed, so we have convergence, and that means we have found the optimal v star values. For part 3, we're asked to find the optimal policy given our values. We've talked quite a bit on which actions give us the better values for each of these states, so let's just name them off. For state 0, obviously we should draw. For state 2, we preferred drawing. For state 3, we wanted to stop. For state 4, we wanted to stop. And for state 5, we wanted to stop. So this is the optimal policy pi star. For part 4, we're asked to run one step of policy iteration. Just a quick explanation on policy iteration, we start with some fixed policy pi 0. Then we repeat the following process. At iteration I, from 0 onwards, we run policy evaluation to get the optimal values for every state following our current policy pi I. It works quite similarly to value iteration, except the max over all actions drops because we're confined to taking the action as dictated by our policy. After we run this kind of iterative process and the values for v pi of I converge, we run a policy extraction step to use these values that we just generated to compute a better policy. The key point is that the values v pi I are only as good as the policy pi of I gets. If the policy is not great, then some of the values won't be that great. But when we do policy extraction, notice here we have an argmax over all actions. That means we have the freedom to choose among the different actions, and this can help us potentially switch from bad actions to good actions. So we repeat this process until the policy converges. In this problem, we're given an initial policy in this row. We need to run policy evaluation to get the optimal values following that policy, so we can run the iterative approach here to compute these values. Or we can just reason about what the best values of acting on the policy are. Let's do the latter. The stop actions are easy because once you stop, you get the value, so let's just fill those in. The stop for 2, you get the value of 2, and then if you stop for 4, you get the value of 4. The draw actions require a bit more thinking, so let's start with thinking about state 5. Our policy tells us to draw, so we have to follow it. And if we follow it, we're guaranteed to get a hand that has a point count of 7 or higher, so we land in the done state, and we don't get any rewards, so this value is going to be 0. For state 3, our policy also tells us to draw, so we have to follow it. The successor states are 5 and the done state. We just said that starting at 5 gives us no utility, and the done state gives us no utility. and drawing gives us no utility. So no matter where we land in from state 3, we're getting no utility, so we can put a 0 here as well. For state 0, our policy also tells us to draw. Here, we can land in state 2, 3, and 4. The first draw move gives us no reward. If we land in state 2 or 4, we're forced to stop and get the values 2 and 4 respectively. If we land at 3, well, we're forced to draw again, and as mentioned earlier, if we draw from 3, we're getting no utility. So we take an average over these 3 cases, meaning we take an average between 2, 0, and 4. That comes out to 2. So these are our optimal v pi I values. Now we run policy extraction to get our pi I plus 1 values. Here we have the freedom to consider both actions from each state, but we have to use the v pi of I values as the future rewards. Let's work from right to left. For state 5, we can either draw and get a utility of 0, or we can stop and get a utility of 5. Well, 5 is higher than 0, so we will want to stop in this case. For state 4, we can continue to stop and get the reward of 4, or we can now choose to draw. If we draw, we're guaranteed to get a hand that has 6 or higher points, so that gives us a reward of 0. Hence, we should continue stopping. For state 3, we can stop and get a reward of 3, or we can continue drawing. And if we continue drawing, we'll get a reward of 0. Notice that drawing still yields 0 utility because we're using the v pi I values, which means we're still stuck with the value from the old policy that said to draw at state 5. So we'll choose stop here because 3 is higher than 0. For state 2, we can continue stopping and getting a reward of 2, or we can try drawing. If we draw, 1/3 of the time we land at state 4, 1/3 of the time we land at state 5, and 1/3 of the time we land in the done state. Landing at 5 and the done state give us no utility, and landing at state 4 gives us a reward of 4. So on average, we get an expectation of 4/3. 2 is higher than 4/3, so we'll choose stop here. For state 0, if we stop, we get a reward of 0. And if we draw, we get an average of the values at state 2, 3, and 4, which is an average between 2, 0, and 4, which is 2. Hence, we should draw here. And here's our pi I plus 1 value. This concludes one round of policy iteration. For the last part, we're asked to consider a variant of the game with a discount factor of 0.5. And we're asked to compute the optimal values and find the optimal policy. So what does the discount factor do? Well, basically it pulls down the value of our rewards as time passes. So if we wait to get a reward, then the value decays. Keep this in mind. If you remember from the results after running value iteration with gamma equals 1, then these are the results that we got. For the states that we stopped at, that is 3, 4, and 5, we're going to continue stopping in this new variant because adding the discount factor only serves to decay our values in the future. But if the stop action was already preferred in the original problem, there's no reason that we want to draw in the new problem. Not only because it's suboptimal, but if you draw, the values decay anyway, so it's like hurting you twice. So the optimal actions for state 3, 4, and 5 is to stop. And the values that you are going to get are going to be the same as the ones above here because the values don't decay on the first turn. They start decaying after your first turn. Great. Now let's consider v star of 2. In the non-discounting case, we preferred drawing since we could get a value of 3 as opposed to stopping, which gives us a value of 2. Now with the discount, the value of 2 for stopping still stays the same because it doesn't get discounted on the first turn. But if we were to draw first, after one turn, our rewards would be discounted by a factor of 0.5. So in the non-discounting case, if we drew and we landed at 4 and then stopped, we would have gotten a reward of 4. Now we get half of that, which is 2. Similarly, if we landed at 5 and then stopped, in the non-discounting case, we would have gotten a reward of 5, but now we get half of that, so we get 2.5. And then lastly, we have the case where we drew a 4 and then we busted, well, we're going to get no reward, so discounting doesn't really affect a utility of 0, so we'll put 0 here. And then we just take the average of these because they happen with equal probability. The average equals 1.5. So between these two, 2 is greater than 1.5, so the value here is 2, and we would prefer to stop. Lastly, let's consider v star of 0. Well, stopping gives us a value of 0, so drawing is going to be preferred since we can at least get some value. To compute the value for drawing, we look at the successor states, which are 2, 3, and 4. At these states, we decided stopping was the best, so after drawing from 0 and landing in any of these states, we're guaranteed to stop on the second move if we're trying to act optimally. So if we land at 2, we get a reward of 1. If we land at 3, we get a reward of 1.5. And if we land at 4, we get a reward of 2. The average of these is going to be 1.5. Hence, between 1.5 and 0, 1.5 is higher, and so we would prefer the draw action. And that's it.